Hello everyone, I'm Evelina Juntunen and this is Introduction to Flexible Optoelectronics Manufacturing. First slide, I give the outline of this presentation, already introduced by Edward also. So first there is a short introduction part, and then I will go to manufacturing and go through the main steps, most important things related to manufacturing, and then I end with conclusions. So what is flexible electronics? Shortly, it is making electronics on a flexible, transparent foil substrates. And it's typical to this technology that the foils are produced in roll format. That means the manufacturing methods are using large area, high volume printing like mass manufacturing methods that are very typical. Also, some additive patterning methods similar to standard PCBs are also used. So what is a flexible optoelectronics then? It is such a technology with optical features. So optical components, and these basic components, how to do it would be either a flexible OLEDs or putting normal LEDs on flex that we call hybrid. And next I will start by introducing these both categories shortly, starting with OLEDs. So OLED is a short name of organic light emitting diode, and basically it is this kind of flat sandwiched structure of of layers put on top of each other in between two conductors. And these layers are organic carbon-based thin films. And when current is applied, light comes out. So it's electroluminescence phenomenon. And typical applications of OLED technologies are displays that have very great picture quality, brilliant colors, fast response rate, and wide viewing angle. The other application for OLEDs is for lighting. The benefits of the technology are that they are very thin, efficient, and without any so-called bad metals, as this is organic materials that are used. This is some very typical example of OLED technology today. So Samsung is probably the biggest producer of commercial products. These mobile phones and tab computers, they use OLED technology in their displays, and at the moment are already producing millions and millions of such displays. The other big commercial producer is LG, also providing displays, but mainly more concentrating on TVs that are nowadays already on the market and very, very thin, and prices are also coming down. Regarding lighting, many big producers like Philips, LG, GEM, Osram, Konica Minolta are providing OLED panels. But let's say that production capacity is still rather low and prices are high. Although, like mentioned, the devices already exist on the market, like this LumiBlade shown in this picture. Also, this kind of a big installations have been done all around the world. Here is a couple of examples from Malaysia and Japan, showing this kind of a large area lighting with OLEDs. So here's the technology. There are two basic ways of making OLED. The first one is called a polymer OLED, that is based on wet processing, that kind of gives the basic features of this technology. It is a simple device architecture, so there is a potential for low-cost processing, but the challenge is that efficiency is not as good as with the other technology. The other one, called small molecule OLED, is the technology that has made all those commercial examples I just showed you, and it uses vacuum processing, so it can make more optimized layers, so there are multi-layers possible, and consequently the efficiency and the lifetime is better. The drawback of this technology is that because it uses vacuum, it is a slower process and also more difficult to scale to large area. But both technologies today exist, and this is I work at VTT, and we develop these components, and this is just an example list of things that we have done here in research. So we have done OLEDs and other printed components as well, like organic photovoltaics, that are solar panels, and transistors, batteries, sensors, and memories, and so on. VTT makes these components printed, so we use this polymer OLED approach in our work. So the other, that was the OLED part. The other category is hybrid systems that is related to this Optintegral project that is organizing this webinar. What hybrid system means, it starts with printing roll-to-roll, making the transparent flexible foil, and of course you can print components like I just introduced, or you can print passives and OLEDs and solar cells and so on foil. But it's common that these printed components don't have the performance up to the level that the discrete components have. So it's common approach to put also discrete components like LEDs or ICs or sensors or something like this on these foils. And these structures are called flexible hybrid electronics. Flexible coming from the flexible nature of the foil, and hybrid meaning that there are organic and inorganic components on the foils. Such electronics is also compatible with overmolding. That is a mass manufacturing technology of making plastic parts, and when combined with electronics, these plastic parts can also have electronic features as well as optics and mechanics and such a 3D features that overmolding brings to the device. So the added value of such integration is of course the reduced complexity, as everything is put in one process and in one package. So there is less mechanical parts and just a single substrate implementation. Of course, the volume and size and weight is reduced. It is a seamless integration, so they can be optics, electronics, and mechanics all in the same structure, very nicely combined without any additional vias and interconnections that are used in normal electronics constructions. This is a technology that can do 2 dimensions and 3 dimensions geometry, and also the value chain is simplified as there is less subsystems to deal with. So many nice features of the technology. This is more new compared to OLED that I just introduced previously, but already some commercial examples exist. Here you can see most of the commercial things are some kind of a control panels and intended for for vehicles industry, because they benefit from the 3D lightweight feature of this technology. So these are kind of a typical application is capacitive touch sensors integrated to plastic. From VTT side, we developed this technology, and here are again examples of things we have done. So we have done hybrid way, large area luminaires and displays, sensors and user interfaces, and they are typically intended for wearable systems and healthcare applications, and also different kind of sensor applications are also. have been done. Yes, so this was the short introduction to these categories, and now I will go to the actual topic of how to manufacture these things, so flexible electronics manufacturing. Here I show you, you can see a couple of videos that shows the basic steps of the manufacturing process. So it starts with printing, and it's this kind of a roll-to-roll processing similar to pulp and paper industry maybe. And then it's typical to pick and place, assemble some additional components to increase the performance of the printed foils. And as introduced just a second ago, such structures are also compatible with injection molding that is sometimes combined with this manufacturing process. So here is a pilot manufacturing environment that VTT has. You can see that we have a different size of printing machines and also different environments, meaning that we can print in air or as inert. And then there are testing and bonding machines that you need, and there is also this injection molding mentioned. Here this is a lot of steps, and this is trying to show how to design and prototype such structures. And of course it is similar to standard electronics. The main difference is that the manufacturing process affects also the design of the devices, so you have to consider the manufacturing process a bit earlier maybe compared to traditional electronics. But of course it starts with the concept that you are trying to develop, and you have to select components and materials and made system architecture. But this is a first step that you should really consider: manufacturing process flow, how you are going to make it. Then you can go to prototypes. Design the prototypes more carefully. That means electronics and optics and mechanics and thermal and all the features that your device will have. And then you can go actually making the prototypes, but it might be that you need to consider also the manufacturability, testability, or even develop some manufacturing process if something that you are trying to do is totally innovative and novel, like we have done in this OptIntegral project. But well, with a prototype you are already quite close to the product. You just have to go to the final step of testing the prototype and making sure that it's what you wanted, and it's also feasible for technical and economical way for your purposes. Yeah. So in this slide, next slide, compared to conventional electronics and especially PCB design, it is similar, but there are some differences that you should consider when designing these kind of new structures with this technology. First of all, the scale of dimensions is huge, because the smallest parts could be micrometers, that are the patterns that you have on your foil, but in the end you can have meters of kilometers of foil in the end. So there are a big range of dimensions. You should remember that bending and stretching also affects the component, the wiring properties. You should remember that printed components typically have a lower performance compared to the discrete or silicon integrated counterparts. And also printed conductors have higher resistance than copper wires that are typically used on standard PCBs. So here you can see a selection of flexible substrate materials, and as you can see there are many choices, and they have a bit different properties. I have highlighted a couple of important ones with red marking. The PET, the PET foil that I marked as for general use. This is something that we most typically use. It has an okay features, nice features, and it's quite low cost. The PC is handy because it's good with thermal forming. That is something that you need, especially when you are doing integration with plastics. And also the polyimide PI is highlighted because it is compatible with soldering. The other foil substrate materials listed here are also in use, but maybe more or less limited applications or different applications, like ITO-PET that is needed for active components manufacturing, like OPVs or OLEDs. Yes. So conductors, when you have your foil material selected, then you have to select what is the conducting material that you put on it. And there are two ways. Let's say the industrial way of doing this is based on metal laminate. So it makes metal conductors similar way to standard PCB manufacturing. So it's a metal laminate on a flexible foil, which is then patterned and etched. And it sometimes uses also printing methods to make the patterning. So it can be also this kind of a hybrid. But anyway, the conductors would be metal, typically copper, sometimes also aluminium. And consequently, the substrate material underneath is polyimide, that is most widely used substrate. Due to compatibility with soldering, that is also good to have in many applications. The other way to go would be printed conductors, and the positive feature here is that it's additive manufacturing process compared to the etching that you need to do with the metal conductors. And printed conductors are typically materials with particles inside a binder, and the particles are typically metal to make the conductivity. By far the most common metal is silver, but sometimes also copper and aluminium are used. There are also some particle-free metal inks, and for special purposes also conductive polymers. These are especially needed for OLEDs and such that need transparent conductors, because the whole structure has to be transparent. Well, the drawback of the technology is that because there is this binder, so it's not full metal, there is a loss of conductivity compared to metal conductors. In this slide, you can only see images of both technologies. So you can see that on metal conductors, it's typically copper, and on polyimide, that makes this the foil kind of a opaque. I mean, it's not perfectly clear substrate. On the right-hand side, you can see printed conductors with the typical applications. So it's very transparent. It's typically silver, and it's a bit different outlooks also. Well, yeah, and here is a collection of printing technologies that we have been using. I won't go to details, but shortly, you need a way to transfer the ink, that is the conductive part, to foil somehow. And in engraver printing, it's this kind of a engraver cylinder is used that transfers the ink on a foil. Same way, flexography works in the same way, but there are more cylinders, and also the materials are a bit different. Whereas in screen printing, you have to squeeze the ink through the screen that has the pattern that then makes the image on your foil. And screen printing is shown here both in as a planar and as a rotary, so roll-to-roll method. Inkjet is probably known to everybody because it reminds of a typical printer that many people have in their homes. And then there is a couple of coating methods that can be used for coat materials on foil. And finally, there is mention of hot embossing, that is to make this kind of a 3D shapes like channels for bio applications, for example, on foil. Here, again, is a collection of methods and some recommendations and comments. The Graver printing is useful for high volumes because it's quite stable. It can reach quite nice accuracy. The reasoning not to always use Graver is that it's quite expensive tooling compared to flexography or rotary. For that reason, for example, in this Optintegral project, we have been using rotary screen process that is marked as for general use because it can reach the dimensions that are typically needed for flexible electronics nowadays, and also the tooling costs are moderate, let's say, compared to Graver, for example. Flexography has also cheaper tooling, but it's not the accuracy is not always what you need. Inkjet can be used. It's often considered slow because you have to print like you have to kind of draw with the printer head your designs on foil, so it's not that fast process. And hot embossing is the method that makes the 3D channels and such on foil, so it's handy for microfluidics and optical features that are sometimes needed for flexible electronics. And here, just a comparison of different technologies. The message here is that, of course, it is you have to select if you need a very high resolution, so very small prints on your foil. Of course, the printing speed would be slower. The printing speed often correlates with the cost of the manufacturing. So it's you have to select between resolution and speed and cost in your manufacturing process. The other choices that you have to make or other things you have to consider are run length. That means how much of the device you are going to manufacture. What is the print quality that you need and the conductor properties? What is the thickness of the printing layer that you need, and if there is some requirements for the substrate. Sometimes, for example, end user would like to have a paper instead of plastic or something like that. And of course, if you need some personalized information on each copy or each device or not. Well, when you have, now we have gone through the selecting the foil and printing the conducting material on foil. So the next step would be to assemble components on it. And this is this simple graph here is an illustration of a process that we use. It shows that it's a roll-to-roll process, but it works in a stop-and-go mode in a way that the foil is opened on the area of the machine so that dispensing the conductive adhesive, assembling the component, and then curing the attachment with heat and pressure are done in a stop mode. And when this is finished, then the foil moves forward, and this procedure is repeated for the next set of components. And yeah, here you can also see some typical times and some typical parameters that we use for our processes. And this is the machine. I know here's a lot of information, but you can see the web, that is the foil in the middle. And then there are different heads, UV curing head and pickup and bonding head that attached to the components that are either on wafer, like there is a wafer magazine, or there are on this kind of a roll feeder for components. And then there are, of course, camera systems that you need for alignment and dispenser and heating and so on, that you need for this, all the things that you need for the to achieve this assembly process. And again, here's a list of typical components for roll-to-roll assembly. For this project, I marked LED SMD. This means that the LEDs are packaged LEDs. This is common because, of course, we could bond also bare LEDs as bare dies, but this often requires clean room facilities for the manufacturing process. And even though VTT has this, as we are a research institute, typically our customers don't, so that's why we prefer packaged LEDs, because they are easier to handle in industrial manufacturing. Also, with the same process, you can attach some more intelligent components like ICs and RFIDs, but what you often need is you have to remember also capacitors and resistors, so very common components. One difficulty would be the connectors. This is kind of a bottleneck of this flexible electronics manufacturing, because it's actually rather difficult to solve the issue of connectors of such structures that are already very flexible and lightweight. And here is collection, what we have done here at VTT. We have done, we can do many different substrate materials and use different adhesives. And we can print conductive inks and also insulators, both sheet to sheet and roll to roll, also with stretchable materials. And also the adhesive can be either dispensed or printed on the foils. And different components, bare dies and other thin form factor components are used. Thin form factor is typical because it means that it is bendable, and this is often the benefit that we would like to have with the flexible electronics. So that's why thin form factor is typical. And of course, when you do this kind of research, you have to optimize the process and study it with experiments, and also do some reliability testing and so on. Yeah, the final step of this manufacturing process was overmolding. There will be another webinar concentrating on this topic, organized by Optintegral project. But this is just a short introduction to this topic, because it closely relates to flexible optoelectronics manufacturing. So roll-to-roll overmolding is a process where this kind of foil that we just made is fed into the tooling and overmolded in injection molding process with a thermoplastic resin. And the end product is an integrated plastic electronic system. This is a well-known, the injection overmolding is a well-known manufacturing method, and there are many names. It is known also as in-mold electronics or structural electronics or film insert molding. It is commonly used for graphics integration, known as in-mold labeling or in-mold decoration techniques. And here what it really is. So it is a process where thermoplastic resin is injected with heat and pressure. And the resin solidifies when cooling, and it's also reversible, so it can be recycled. And the main process steps are first, you enter the thermoplastic granulates into the barrel where they are melted and injected into the mold tool. And in the molding part, this the plastic solidifies and cools down and then gets the shape of the mold, after which the device is ejected from the tool. Here in this slide, this is a process for how to do this roll-to-roll way. This is a novel, that's something that we have been working on in this project, because it's typical to insert the foil inside the mold as a sheet. But this shows that, okay, it can be done also as a still in roll format. You can see in the first step, there is this foil coming from up to down in a blue color. And of course, it has to attach or clamp to the mold. And then the mold closes and the resin enters to this cavity. And when it's ready, when it's cooled down, the mold opens again and the clamps opens and you get out of your device that you have been overmolding. Yes, and this is just an illustration of the machine that we have. It's let's say industrial scale machine, but we have integrated a foil feeder to the system so that we can really do roll-to-roll overmolding experiments like we have done in this OptIntegral project. The clamping force is the basic way of identifying how big devices you can manufacture with your machinery. And here are demonstrators that we have done here at VTT over the years. We have overmolded OLEDs, displays, and OPVs, that are the solar panels, microcontrollers. We have made this kind of a capacitive touch sensors and light guide optics over the overmolding. Also, we have used overmolding to form battery compartment and connector structures, so these kind of mechanical structures on electronic devices. So I'm reaching my conclusions. So today I have been talking about manufacturing process of flexible optoelectronics, and I have introduced those steps that are bolded in this slide. So we have been talking about how to print passive and active components on foil, how to assemble components on it, and how to overmold it. And the other steps here in this slide are related to how to manage with the foil in roll-to-roll way. So basically, like there are steps like foil perforation that is needed if you need bias through the foil, or cuttings on your foil, or your carrier foil is sometimes needed if you have many cuttings or something like that on your foil. And of course, there is always some manual assembly, but the point in this roll-to-roll manufacturing is that it minimizes the manual steps and makes the process throughput quite fast. And here is a collection of typical materials that we have experienced. The requirements for the selection are system requirements, chemical compatibility, and processability. But here are mentioned the flexible substrates that are typically used, PET being the most common. The silver filled polyester conducting paste is the most common printing paste that we use. For the adhesive bonding, the would be modified epoxy, that is one component heat curing anisotrophically conducting adhesive, that this is the most common adhesive that we use, and for the overmolding, thermoplastics are PC and TPU that are the most common. Yes, I'm about to finish. I just want to say that VTT is part of this kind of a Printosent Innovation Center that commercializes technologies from lab to markets, and we have been part of this work almost a decade already, building up this infrastructure of manufacturing these thin organic flexible electronic devices. And we have this kind of industry cluster around us. So this is a cluster of companies and research with a common interest on Tola-IA electronics. But this pilot factory is open access for everyone. So it is available if somebody has an idea of a Tola-IA device but don't have the manufacturing capability or the knowledge in-house. So you can come to this Printosent pilot factory to make your products. At least for pilot your products, it's not really commercial manufacturing, but it's for development purposes. Yes, so I'm finished with my presentation. I'd like to thank you for your interest in this, and most of this information is borrowed from Printosent Designer's Handbook, so there is more information if you're interested, and also some other scientific references that I have used to make this presentation for you are listed here, so you can look up if you need more data. Thank you.